today's session, we'll explore a crucial technique that has transformed machine learning, particularly when working with a small dataset. Imagine trying to build an image classifier for rare disease when only a few hundred medical images exist. Or training a self-driving car model when real-world driving scenarios in bad weather conditions or poor road traversability are costly to collect. How can we build accurate models with limited data? The answer is transfer learning. And what is transfer learning? Let's think about learning a new skill. Imagine you have mastered playing the guitar. You understand chords, rhythm, and timing. Now you decide to learn the piano. Because of your existing musical knowledge, learning the piano is easier than starting from scratch. This is the essence of transfer learning in machine learning. A model trained on one task, known as the source task, is reused or adapted for a different but related task, called the target task. Instead of training a model from scratch, we leverage knowledge from a pre-trained model and fine-tune it for the new problem. Imagine a deep learning model trained on millions of general images from sources such as ImageNet. That model can be fine-tuned to classify medical X-ray, even if we only have a few thousand labeled X-rays. Why is transfer learning important? Transfer learning is a fundamental technique in machine learning that allows models to leverage prior knowledge from one domain, source, to improve performance on a different but related domain, target. The theoretical foundation of transfer learning is based on the idea that learned representations in deep neural networks can generalize across tasks, reducing the dependence on large labeled datasets. Transfer learning helps mitigate the challenges of training models in data-scarce environment by 1. Reducing the need for large labeled dataset. Traditional deep learning models require millions of labeled samples to generalize well. Transfer learning reduces this dependency by leveraging pre-trained representation, enabling effective learning with fewer annotations. Second, speed up training. Instead of initializing model weights randomly, pre-trained weights provide a strong starting point for optimizations. This allows models to converge faster, requiring fewer epochs and less data to reach optimal performance. Third, generalization and accuracy. Deep neural networks trained on large-scale datasets, such as ImageNet, JFT300M, learn generalizable feature hierarchies. Fine-tuning such models on smaller datasets preserve useful features while adapting to task-specific nuances, leading to higher accuracy. And 4, lowering computational costs. Training deep networks from scratch requires massive compute resources. Imagine thousands of GPU hours. By reusing pre-trained models, transfer learning significantly reduces computational overhead while achieving comparable or better performance. Now, let's break down 3 key categories of transfer learning and their applications. First, transductive transfer learning, which means same task, different domain. Here, a model trained in one data distribution is adapted to work in a different but related data distribution. Example includes domain adaptation and zero-shot learning. Second, inductive transfer learning, different task, related domain. A model trained for one task is used for a different but related task. Example include a deep learning model trained for object detection, for example, detecting cars, is fine-tuned to detect pedestrian. And third, unsupervised transfer learning. Focus on using unlabeled data. This approach doesn't require labeled data, making it useful when labeled datasets are very scarce. Autoencoders and generative adversarial networks can learn latent representation from large unlabeled datasets and then be fine-tuned on very small labeled datasets. As we progress, I encourage you to think about how would you apply transfer learning in your field of interest? what challenges would arise? Would you encounter domain shift, dataset biases? What pre-trained model would you use? Do you use ResNet for vision, BERT for NLP? What else? Now imagine if you were working on infant sleep monitoring with limited real-world infant video captured by commercial baby monitors. How could transfer learning help? What adjacent domain datasets would you pre-train your model on? Adult sleep data, data from awake infants, data from an infant avatar? How would you adapt it? Engaging with these questions will deepen your understanding and prepare you to apply transfer learning effectively in real projects. As AI continues to evolve, transfer learning remains one of the most practical and impactful techniques in addressing small data challenges. Use it wisely, and you can build powerful models even with limited data.